Good morning, everyone. Welcome to the second day of ICAPS. This morning, we have the pleasure of have Chris Beck as our invited speaker. Chris Beck is a professor at University of Toronto. His work spans in many areas. Okay, he's been before working in ILOG for 3 years. He also spent some time in the Cork Constrained Computational Center. He's got more than 100 papers in scheduling, optimization, hybrid planning, I guess, MIP. So he spans across several areas. He's been the president-elect of ICAPS. He's been co-chair of CP, CPIOR. And I think that if there is few people with expertise that actually bridge us, our community, with constraint programming, optimization, and well, we are looking forward to hear your talk, Chris. Thank you very much.
All right, thank you. Thank you for coming out on Sunday morning, and thank the organizers for inviting me. So when I looked at the other invitees, I realized it was going to be rather difficult to compete. And so rather than talking about sort of application stuff where I'm certainly not going to compete, I'm going to go completely the other way and talk about kind of really abstract stuff that I like to do to try to understand some of the details that's underlying search. And so I'm going to talk about the work that's mostly done by one of my students. This is Eldon Cohen, and this is one of the pleasures of being a professor is somebody else can do all the work and you get to come invited to give the talk. So last night, the organizers, after the industrial session, invited some people out with the industrial people to a Chinese restaurant. And of course, at the end, we had fortune cookies. And my fortune was this, which is like twice interestingly coincidental, right? Both planning and the fact that I had to go home and revise all my slides last night. So I'm going to talk about empirical algorithmics. That's not pink, by the way. That's a 1980s joke for those of you who might get it. So why do algorithms behave the way they do? In the end, since we're solving NP-hard problems most of the time or worse, we're going to lose. But sometimes we win, and maybe we want to understand where we win when we do win. And this is not a particularly new idea, especially in the heuristic search literature. I mean, there's people that are looking at algorithms as kind of elements of the natural world, and from kind of a natural sciences perspective, try to understand and model what these algorithms are doing in order to provide us understanding, but also to then allow us the next step of maybe improving some of these algorithms. So that's the perspective I'm going to take here. When Eldon came and started working on this, I told him he's not allowed to create any new algorithms, which is a really hard sell for anybody. And unfortunately, there's a footnote that's off the end of the screen, so you're not going to see the jokes in the footnotes, but anyway. And this is no new algorithms, but rather algorithms are tests of hypotheses. So we want to do some work. We want to try to make a hypothesis about what is causing some behavior we're seeing, and then design an algorithm that, if our hypothesis is correct, or if the algorithm works out, we actually have some support for the hypotheses that we're making. So we're trying to make a very kind of classic science approach to this. We're not that interested in solving better problems right away. That will come later. I am going to talk about a few algorithms, but they're really straightforward, simple algorithms because they're designed to test the hypotheses that we're making. So I'm going to talk about two pieces of work, really the second and third one. But in order to talk about two pieces of work, I need to give you some background from the 1990s. And the professors out there should be careful about giving their students papers to read, because the only papers I remember are the papers that I read in the first couple of years of my graduate school. And so that's what I always talk about. So this is a paper from AAA, from AIJ, 1996. What you see here is a set of random three-sat problems. Okay, so each point here is the result of, I can't remember their number, let's say 1,000 problems that were generated with at a particular size with a particular clause variable ratio. And what you see here are two graphs, right? The one up here, if I can see what's going on, this is the solubility of the problem. So when I generate a problem at this point in my instance space, what's the probability that it actually has a solution? Okay? And what you see here is at this end, with a low clause, says clause to variable ratio. With a low clause to variable ratio, everything's easy. Okay? What you can think about this in sort of more general terms, in an under-constrained problem, everything can be solved. Okay? When we have over-constrained problem, we've added more constraints, we see that none of the problems, none of the instances at those points actually have solutions. And so the solution, the result here is proving that it's unsatisfiable. And then what you see here is this curve, which is a normalized curve about search effort. And you see where it's under-constrained, it's easy to find a solution. Where it's over-constrained, it's easy to prove no solution exists. And what you have in the middle, okay, is where the hard problems are. Okay, and so this transition between soluble and insoluble is called a phase transition. And there's been a whole lot of work through the 90s on SAT and CSP that talks about how we see this spike in the difficulty of the problems where this phase transition happens. And there's all sorts of deeper math about this, about what happens as we extend the problem size. And there is some fundamental mathematics underlying this. I'm not going to talk about it. So the work that actually really kicked this off was a previous work. This is from 1991. This is Cheeseman and al. From ICAPS. And they made a number of conjectures about NP-complete problems, that all NP-complete problems have an order parameter, and at a critical value of the order parameter separates regions from under-constrained and over-constrained, and that the hard problems are found in this critical value. And so that was the hypothesis, the conjectures they made coming out of this ICAPS paper, which kind of led into, this was 1991, which led into about 10 years, almost 15 years of work on understanding kind of empirical hardness of these problems in constraint satisfaction and SAT and some other areas. Mostly sort of not planning problems, but the classical constraint satisfaction problems. And so we said, so what about heuristic search? And so a few years ago, we decided to say, well, we're going to take the actual underlying state transition graph for a heuristic search problem, and we're going to suggest as our order parameter this gamma, which is the expected number of edges in a transition graph over the total number of states. And we're going to vary that, so we're going to produce problems along this horizon and see what happens in terms of our results. And so this is the Pancake problem. Okay, if you don't know the Pancake problem, don't worry. Just think of it as a heuristic search problem. And this green line, which I hope you can see right here, okay, this is the actual Pancake problem instance that is defined in the literature. And what we did was we actually took the state space and started to manipulate it by adding new edges in our state space. Of course, the Pancake problem is a particular puzzle, and we're doing strange things because now we can kind of we can teleport from one state to another because we've added in an extra edge. On the other side, we start removing edges from this underlying graph. Okay, and what we see, all right, so let's first look at the black line. Okay, this is the existence of a solution. Okay, and we see as we vary this gamma parameter, as we remove going this way or add edges going this way from this green line. And again, all of these points are multiple instances. So we decide on a gamma value compared and generate 1,000 instances. And what you see here in the black line is this solubility phase transition. And on top of it, you see the blue line, which is the median search effort over these problems. And you see, again, it's adding up, it's piling up pretty nicely against this phase transition point. So this was 2017. I think this was a SOX paper. What we subsequently went on to do is exactly what the constraint programming and the SAT people did, is they looked at what's going on right here. So what you see, better if I roll it back. So this blue line is the median search effort. This red line is the maximum search effort over all these problem instances that we're running. Okay? And one of the things that people have looked at is at this region here, right, basically in this case at the edge of this what we call the mushy region. The average problem is very easy, right? It's like 20 nodes to expand, okay? But the most difficult problem is, what is that, 15,000 nodes? And so what you're actually seeing is in a region of the instance space where almost all the problems are really easy, you get some problems that are actually orders of magnitude harder to solve, okay? And so the question is, what's going on here? Why do we have this phenomena? This phenomena came to be called the exceptionally hard problem instance. This is another look at the same graph, okay, or the similar results where we play it out a little bit more and put it on a log scale. And again, you see at this point, we've got the 99th percentile being several orders of magnitude more difficult than the mean. So this was termed an exceptionally hard problem. This is a terrible name because when I start to talk about exceptionally hard problems, people just kind of parse the words and think, well, why is this an exceptionally hard problem? And so it's like, that's why I had a few slides ago, a trademarked exceptionally hard problem. There's a specific meaning to what they call an exceptionally hard problem, and it's this. This is an empirically very hard problem instance in, on average, an easy region of the instance space. And the question is, why? Is this really a hard problem? Or is there something going on that we could understand what is going on to make this difficult? Okay, so in 1998, Carla Gomes ran a couple of experiments, okay, and the first experiment was to generate and solve multiple problem instances in the under-constrained region, okay, and run a backtracking search until you find a solution. And what she showed, this is a scheduling problem. This is actually a 12-team round-robin sports scheduling problem. And you can think of this as a histogram. This is search effort, okay, number of backtracks, and this is the survivability. And basically what you're seeing, we've got a log-log graph with a straight line, which is kind of nice. This is a classic heavy tail distribution, okay? So what you're seeing is different problems at this same point, in the same easy point in our instance space. Many of them are easy. They don't take very much effort, but you have a non-trivial tail. In fact, it's a heavy tail where these are hard problems. Okay, so that is just sort of confirming what's seen before. And this is a heavy tail distribution. And again, there's some underlying mathematics to actually model this and to actually not just look at a straight line on a graph and say, oh, it must be heavy tails, but to calculate kurtosis and actually show this a little bit more mathematically. The second experiment, okay, is rather than, so take the same point in our problems, in our instance space, take one instance, and then we're going to solve it repeatedly with a backtracking search with a slightly randomized heuristic. So classically what you might do is your heuristic suggests the top 3 choices you could make at this point, and you randomly, with uniform probability, pick one of them. Okay, and so then if you restart and run it again, you're going to get a different path. And the very interesting thing is when you do this, on one problem instance, you get the same graph. Okay, so one problem instance can be out here, or it can be up here, depending upon the random seed that you started with in your slightly randomized heuristic for your backtracking algorithm. Okay, so the exceptionally hard problems, EHPSs, large search effort is due not simply because they're hard problems, some sort of inherently hard problems, like they might be closer to the phase transition, but we've got this interaction between what we're trying to do to search the problem and the problem instance itself. So they're not inherently hard, we don't have the right heuristic, and so maybe if we were smarter about our heuristic, we could actually solve these problems much more quickly. And they went further. This is still the work of Carla Gomes and her co-authors. So this is a search tree, right, a backtracking search tree. The solution to this problem is over here. So this is a satisfaction, I think this is a CSP, but we're just looking for a feasible solution. This is not optimization. The solution is over here, and what we have here is what the search did. And so this is a subtree where there's no solutions, okay? And so it's a failed subtree or an inconsistent subtree, and in a depth-first search, the search actually has to exhaust everything in this search tree, the subtree, before it gets out here back on a good path. It makes another mistake here. Here's another failed subtree until it eventually makes it over here. And what they showed is that the heavy tail distribution occurs exactly when the depth of these failed subtrees is exponentially distributed. And so the green is actually from the hard region, and what you're seeing is that the depth of the failed subtrees that are encountered during search, there's a lot of big failed subtrees. And so there's a lot of effort. These are hard problems. In the heavy-tailed region, you actually have this exponential distribution. And if you're unlucky, you end up with a search that ends up in one of these deep subtrees, and you spend an awful lot of time trying to get out of them. And so they characterize the occurrence of these heavy tails in the empirical results by the existence of this exponentially distributed depth of insistent subtrees. So heavy tail depends on the depths of the failed trubs. Heavy tails occurs when the depth of the failed subtrees is exponentially distributed. All right, so that's what I said about a failed subtree, okay? And so we got thinking about local minima, right? So we took Wheeler's definition of local minima for a greedy best first search, a region that does not contain the goal, but that the search is going to have to exhaust if it enters it. And so we thought this was a pretty nice analogy to the failed subtrees that the CP people were talking about. And we got to think about these questions. Can we find heavy-tailed behavior in planning as opposed to just heuristic search? So I mean, at the work I showed you before is we're actually in there in the graph, manipulating the graph. It would be much nicer if we could look at planning problems, not have to go down to the completely grounded graph level and try to understand if we have heavy-tailed behavior. If so, can we connect it to the local optima? And furthermore, if this all works out, can we get out of this? Okay, so this is the work in heavy tails on local optima and planning that appeared in AAAI 2018, and underneath that you can't see ICAPS 2018. Okay, so our first problem is in CSP SAT, the phase transition has this, is conjectured to appear where the expected number of solutions is approximately 1. So there has been some work that generalizes this idea of the order parameter to try to understand what this order parameter is doing. I'm not going to go into that details, but this is what has come out of the SAT and CP literature. And so what we're trying to think about is if I have a planning problem, how can I figure out what parameter I need to turn on my planning problem that changes the expected number of solutions I have, okay? And so since we're scheduling guys, we immediately think of resources, and since I'm a constraint guy, I immediately think of constraints. And so we're looking at resource constraintedness in planning problems. And so this work from 2012 studied these problems and suggested that we have this parameter C. So C, I understand C is basically the amount of resource that you have where it's normalized so that C is equal to 1 means you have exactly enough resource to actually solve your problem. This is not replenishable resource, you just consume the resource. Obviously, if C is less than 1, there are no solutions. If C is greater than 1, then you have more and more ways that you can actually solve your planning problem. And so we're going to make use of that to try to do the same experiments that have been done in CSP. And so we generate and solve multiple problem instances. So again, this is experiment 1 in that under-constrained region. So what I'm skipping is that whole phase transition and the existence of a peak like we saw in the Pancake problem. It all exists here. I'm jumping to the heavy tails and to looking at this region where it's easy. And what we see is the following. Okay, so we've got 1,000 problem instances, okay, at each value of C. Okay, we're running, I think we're running FF here, okay, and looking at the number of expanded nodes. And what we see at the phase transition, essentially, this red curve, we have no heavy tail distribution. These are hard problems. Most of our problems, right, are taking a fair amount of time. What we see as we relax the resources, as we add more solutions, right, we are seeing in the green and the blue lines, we're seeing this heavy tail distribution, and these are actually the kurtosis values if you're really interested in the stats. But what I'm looking at today is sort of a linear fit across many orders of magnitude on a log-log graph which is basically the indication that you probably have heavy tails there. And so what we see is, just like we saw in CSP, as we relax the solution into easy areas, okay, many of our problems, right, most of our problems are solved very quickly, but we have this heavy tail out here on problems that take an awful lot of time. Experiment, so we have heavy tails, okay. Experiment 2, we need a randomized heuristic. So again, we want to take one problem instance now, okay, and run a randomized heuristic on that problem instance. We actually want to take one problem instance from each of these constrainedness areas and see what happens. And so what we did was we took any heuristic you want in planning, okay, and remember again, I'm talking about greedy best first search. This is the standard, FF, LM cut, whatever we're talking about in those situations. And we're going to randomly perturb what the heuristic is giving us, okay? So based on some delta P, the heuristic value at a state is going to be the real heuristic for the state for whatever heuristic we're using, plus some noise that's uniformly generated in this interval. And of course, our delta P allows us to control the noise. So what we're going to do is we're going to pick one problem instance, okay, one problem instance for each C value, in fact, and we're going to run it multiple times with this randomized heuristic, and we see exactly the same thing. Okay, so this is 1,000 randomized search runs on a single instance with FF, and our delta P here is 0.05. Okay, and so we see exactly the same thing. In fact, it's interesting. Some of the, the hardest, the blue line, the red, which looks like it's where it's at the phase transition. It's the hardest instances there are actually easier empirically than some of the hardest instances from the easier regions, or from the on average easier regions. Okay. So again, we're seeing what the CSP and CP people found, so this is good. No one had talked about this in the context of planning before. Why is this interesting? Okay, so this is all sorts of stuff that's going on with search effort. Because to me it's interesting, one, to try to understand what is search at some sort of fundamental level, to try to understand the behavior of search. But also, if you think about this as one problem and you're interested in solving a planning problem, each of these lines is one problem, and a very tiny change in your heuristic, adding some randomization, gives you orders of magnitude different performance on this problem. Okay, and so in terms of actually solving problems well, it's kind of interesting that you have one problem instance that can have orders of magnitude difference with this tiny change in our state-of-the-art planners. And can we understand that? And once we understand it, can we do something about it? So I only showed you resource constrained. I only showed you, in fact, one instance or one domain. It also works for TPP and rovers. We also looked at other heuristics. We also had another definition of our constrainedness, this knob that we turned to take us from an easy region to a hard region, easy, hard, easy region. And so those papers actually go into more depth. I'm just showing you one of the instances to try to show you some nice pictures. Okay, so we have heavy tail distributions. Okay, this is all the CSP stuff. But now the question is, is there more to this analogy between these failed subtrees and these local optima? Okay, so this is what I showed you before in CSP. Okay, so the idea here is in greedy best first search. Okay, here is the path that search has taken. Only a subset of the nodes visited during the search, of the states visiting during search, are actually part of the plan. Okay, and so with the blue ones, I'm saying are part of the plan. These other ones are states that are not on the path to the plan, but we search through anyway. And the question is, these are actually our local minima that we've worked through. And what we can show is that, and you can't see it's not here. Okay, so this is the non-heavy tail distribution. So the colors actually match up here. And this is our heavy tail distribution with a particular measure of the size of the local optima. And we're going to talk about what that measure of the size of the local optima is. But what you can see again is we're seeing the exponential distribution of that measure. So let's back up and try to explain what that picture showed you. Okay, so local minima in greedy best first search. Here is our path of states that we visited this is their H value, and so nodes visited during search, nodes in an actual plan, okay, and then we have the nodes that are in a local minima. Okay, so these are states that we searched through. Okay, we had to eventually get out of this set of states back to a plan. Okay, we found another small local minima before we went there. Okay, so we're going to talk about the H depth of a local minima, which is defined to be the distance, the subtraction of the first state outside of the local minima versus the deepest state, the lowest H value inside the local minima. Okay, so we're looking at subtracting H values. And we're going to call an H backtrack a point in our search where we've at a state of a particular H value, the following state is actually at a higher state value, so we've backtracked in H. Okay? And so our first thing to try is, well, what does search look like if we start to measure H depth and H backtracks? Okay, and so what we're seeing here is this is the number of expanded nodes in a local minima. Okay, and this is the H depth of the local minima, okay, with a log scale. And so what you see is that in a local minima of a particular depth, we actually have an exponential relationship between the H depth and the number of expanded nodes. We can go a little bit further, okay, and we can look at the H depth and the number of H backtracks. So how many backtracks does it take to escape this local minima? And we also see an exponential distribution, okay? And so we were very happy about this, right? Because it looks like that greedy best first search is behaving an awful lot like standard tree search over these H levels, okay? So this is exactly, we all know about search trees, right? This is exactly what you would see with, a balanced binary tree, an exponential distribution between the number of nodes and the depth. It's not clear to me, or at least I don't think it's necessarily the case, if you think about what greedy best first search is doing, that this pattern is inherently there. If you think about plateaus in the search space, right, there's no reason that I can think of that this isn't at least a little bit surprising to me. Maybe I'm missing something and there's something deeper that somebody will tell me about that says that, yes, this is obvious. But to me, this was interesting result, and also it was a good indication that maybe we're on the right track in terms of trying to bring these CSP search things over into planning. So this slide is for Steve Chen, who I told a number of years ago, about 2 years ago, where I said that in CSP, and I claimed in planning, the depth of the biggest local minima is almost the only thing you have to worry about in terms of search effort. Okay, and so what we're doing here is we're taking a number of these domains. The 1,000 is 1,000 problem instances run with a heuristic. The 1 is 1 problem instance run with a randomized heuristic. This is no heavy-tailed region. This is the heavy-tailed region, and this is the correlation between the H depth of the single deepest local minima that has been encountered and the total search effort to solve this problem. Okay, and so what we're seeing across many problem instances, we're seeing an extremely high correlation between the H depth, the single deepest H depth, and the total search effort. And so my claim at the time to Steve, and this was based on what the CP people had, was that that's the thing that really matters, or to a certain extent matters a lot in terms of solving these problems and in terms of the search effort. And so it's taken me two years to give you a table that supports my my position. Oh, okay. That's hard to publish, though. Okay, so CP and SAT, heavy-tailed distribution arises when the depth of failed subtrees is exponentially distributed. The hypothesis is that for GBFS, a heavy-tailed behavior arises when the H depth of the local minima is exponentially distributed. Okay? And so these are the graphs that you saw before. Okay, this is the non-heavy-tailed regime. Most of the runs are encountering a deep local minima, okay, and that's not where heavy tails show up. Okay, In the heavy tails, right, there's a low but non-negligible probability of having a deep local minima, and this is what's leading to this randomized heuristic, right? Sometimes it falls into one of these things and gets stuck and takes multiple orders of magnitude longer than a different random seed. And because it's the depth of this single deepest local minima, this has a huge impact on the overall search effort that you were seeing in those graphs. Okay, so far I hope you realize that I have no new ideas, that I just take everything from CP and try to map them into planning. And so that's not going to stop, okay? So the next idea is, can we escape heavy tails? And so what do we do in CP and SAT? This is where a lot of the randomized restart algorithms came out of, because it had like a firm basis of what we were trying to do. If we're in one of these deep subtrees, or we think we're in one of these deep subtrees, there's been a lot of work that showed the expected value, the minimum expected subsequent search effort can actually be lower if you just restart from scratch with a slightly different heuristic, because then you, with this exponential distribution, you might get lucky, you will often get lucky and not fall in one of these subtrees. So let's do the same thing in planning, okay? This is back to my no new algorithms, okay? And the star says mostly. So here's my new algorithm. Randomized restarting GBFS. So all we're going to do is run GBFS with some random seed. So this is the slightly randomized GBFS, and a cutoff. The cutoff is the number of H backtracks that we're going to allow in our search, okay? And what we're going to do is we're going to increase that cutoff. So we're going to run it with a small cutoff at the beginning, right? And we're going to geometrically increase this cutoff as we don't find solutions, with the idea being that if we've searched a little bit and haven't found a solution, we might be in a deep local minima, and it's time to jump out and do something else, okay? All right, so here is the standard GBFS, okay? And the dashed line are the randomized restart GBFS. And what you can see, so for example, the purple one, we've got an order of magnitude and a half of reduction, okay, and we're removing these heavy tails. Notice when we don't have the heavy tail, we're actually losing, okay, which is actually good news, right? Because remember, I'm not that interested at this point in solving problems better. I'm trying to understand why, what is the underlying behavior. And so if I have a hypothesis and this works everywhere, even when the thing I'm trying to understand is not present, well, maybe I don't understand what's going on. So it's actually good news that we lose out here, and good news that we win when we actually see the heavy-tailed behavior. That's just to look at the depth to show you what's going on. So look at these first two. This is the no mystery. This is the depth, the deepest local minima we found with GBFS and with randomized restart, and you can see pretty much across the board there's a significant reduction in the depth of the deepest local minima that we encountered during search. And so it hooks back to what I claimed for Steve. Now, of course, there are other randomized GBFSs, and so one of the questions we have is, are they doing the same thing, or is, in fact, what we've uncovered a new structure, a new behavior that we can exploit? And so there's epsilon GBFS, there's type GBFS, and what we've shown here, so the epsilon GBFS is the dotted line, the epsilon randomized restart GBFS, so I mean, if you go back to here, right, we can just stick in epsilon GBFS instead of GBFS and see what happens. And so what we can show is the dotted line is epsilon GBFS, and so you can see that it is changing things. So the green line, for example, epsilon GBFS, as we know, is improving things, okay? But the, where is it? The dashed green line, okay, which is over here, is even improving the epsilon GBFS. And so in fact, these are not exploiting the same thing, and we can therefore usefully combine them. So we have a randomized epsilon GBFS, which has a little bit of randomization, and we can do randomized restart on top of that. It looks to me like there's a significant difference between these heavy tail behavior that we're getting rid of with our technique and what they're dealing with. And of course, there is sort of, the heavy tails are not the whole answer. There is more interesting things going on, or there are interesting other things going on. And so I think interesting other things going on that are in some cases orthogonal, or at least partially independent of the heavy tail distributions. Okay, so there, we're 3 for 3. All we're doing is copying off the CP work, and we've got a few papers, so I think that's pretty good. So the take-home message, and this was sort of the more fundamental things that I took out of this, is we kind of tried really hard to take some of this empirical modeling of tree search and map it over to GBFS. It looks an awful lot like tree search, okay? In terms of phase transition, in terms of heavy tails, in terms of randomized restart. And I think there's some opportunity for a lot more cross-fertilization from understanding tree search and understanding GBFS. For example, for the IPC domains, the IPC instances, is there a notion of this difficulty spectrum? Do we know where they are? Are these actually hard instances from these domains? Or are these easy instances from these domains? And maybe that's something we want to find out. Okay? And more fundamentally, that looking at the empirical analysis, doing this empirical analysis leads to some hopefully fundamental understanding of what's going on. It's not going to lead to a great new algorithm immediately, but hopefully over the long term, this understanding can build up sort of the scientific side of what we're doing and then lead to better algorithms one of these days. Okay, good. So now I want to switch gears, sort of. It's still looking at the same theme in terms of empirical analysis. It's still looking at search, though it's a slightly different type of search. It's really hard these days to get students who don't want to do machine learning. And so, eventually I had to start doing machine learning. But what I explain to my students is, if you want to do machine learning, you have to convince me that we might know something that other people don't know and have like a chance of competing on some level. And so what we know about is search. And so the question is there something we can contribute to the machine learning literature that actually builds on some of the stuff we know about that maybe they don't know about because they know about all sorts of other things that I don't understand. And so this is work on local Optima beam search and neural sequence decoding. So we're focusing on models that learn sequences, which, if you think about planning, is not a coincidence, okay? There's a lot of machine learning work out there that are producing sequences, right? So machine translation, sequence to sequence, text summarization, we have a big paragraph that we want to create a sentence to summarize, image captioning, conversation modeling, speech to text. So there's a lot of work in the machine learning literature on learning models that you can then use to do some of these applications. To give you an example, or at least a kind of a cartoon at the level that I understand it anyway, of the machine translation sequence-to-sequence models. One of the ways they do things, okay, is we have an LSTM, so this is a neural network, okay? What you can't see at the bottom is that this is our English sentence, right? So this is how are you? And what happens is we encode the sentence we want to translate into this LSTM, so one at a time. We then have the encoded neural network, and it gets decoded over here into a sentence, in this case in French, okay? And zooming in on that decoding phase, what's really going on, or at least a level that I understand it about what's going on, is the neural network gives us a probability distribution over the first token that we can use for our translated sentence, okay? And so based on all of our vocabulary words, we have at least notionally this huge probability distribution over all these words. And what we're going to do is we're going to actually choose one of those words, right? We choose one of those words, okay? It gets put back down here into our next layer. And what happens eventually as we get over here, what the neural network is giving us is a probability distribution over our vocabulary based on our input sentence and on the prefix that we've decided so far. Okay, so we've got a joint probability distribution at every step. So to me, this obviously looks like search, right? If we're only picking one word at a time, it looks like a greedy search. We're picking, the highest probability token, and we're searching through this. So maybe I know something that can help this. Exhaustive search is intractable because we have, I don't know, a branching factor of 30,000 or something, so that's not really going to work very well. Greedy search, as I mentioned, is just going to pick the top probability, and of course, once we pick the probability token, we get a new probability distribution from the neural network over the second token, right? What tends to be used in the neural network literature is beam search. So what we're going to do is we're going to pick the top B words that we could choose. Okay, we're going to expand each of them. So we're going to get, a number of candidates for a second. We're going to then take the top B of those again, expand those again. And so at every step, we're essentially looking at the next layer of our search tree and then cutting it down to B of those. And so it's an incomplete search, right? We're obviously throwing away a whole bunch of our children. And it's a greedy search in that it's taking the top greedy rather than the top one. We're taking the top B. Okay, so beam search is an old idea. It keeps coming back every 15 years or so. And last time it came back that I remember in the planning literature was about 2006, so I guess we were due for it to come back again. But it's also something that I'm not sure why historically, but the machine learning people seem to be using it a lot. And I don't really know why that's happened, but it's there. Okay, so one of the 6 central challenges in machine learning, you always love papers that say things like that, okay, is this problem of beam degradation. And so what they've observed is if you increase the beam size, you get more probable solutions, which you'd expect if everything's working. But those solutions actually have a lower evaluation score. And so in many of these cases, what they're finding in the search is they are finding a highly probable sentence, if we're doing machine translation, but then they evaluate that sentence on an external evaluation. BLEU scores is what they use in machine translation. And what they've shown is if you extend the beam, you actually get worse solutions at the end when you evaluate them. Okay? And at least some people think this is a very important problem in machine translation. These are actually our results to verify what's gone on in the literature. So this is the beam size. These are the metrics. These are, so this is a machine translation from English to German, English to French. This is a text summarization. This is an image captioning. And what you want is you want higher is better. Okay? And what you're seeing here is at beam 5, we're getting much better performance overall than at beam 250. And this has nothing to do with search effort, right? This is just the quality of the solutions that are coming out. So this is the baseline of what people are seeing in the machine learning community. Okay, I want to emphasize that the search objective and the evaluation score are not the same thing. So the search objective is to maximize the probability of the hypothesis, the probability of the sentence, okay? And so it's doing that, right? Beam search is maximizing the joint probability. The problem is that the evaluation score is actually lower when we have a higher probability sentence. So there's some sort of mismatch going on there. And the machine learning people want to understand the mismatch, right? So they're interested in building a better neural network, so there's a better matching between the highest probability and this evaluation. I don't understand any of that stuff, so I'm going to try to figure out, can we actually deal with this mismatch from a search perspective? The overall system is doing machine learning and then using the neural networks as, at least in my abstract level understanding, as essentially a search heuristic. And so if we look at it in that way, can we start to explain what's going on here from the search side of things and then maybe do something about it? So, and those of you who know about combinatorial search, know about limited discrepancy search, what we're going to do is we're going to take this idea from CP and SAT and tree search-based approaches of a discrepancy. And as you can see, all of my ideas come from the 90s, from somebody else's work in the 90s. And we're going to see if we can take this idea and map it into this problem and using it as a lens in which to analyze the behavior that we're seeing. So jumping into the actual machine learning world to define what a search discrepancy is, the greedy choice of a particular token, okay, given the tokens we've already chosen, and the input, the greedy choice is going to be the choice that maximizes that joint probability, or in this case, the log probability. Okay? And so a search discrepancy, if we look at a solution, we look at a point in a solution, is any point where we didn't go with what our greedy solution told us to do. Okay? So we chose a token that had a probability that was lower than the maximum probability token. Okay? We can also define a discrepancy gap at a position, which is basically the distance in probability between the greedy heuristic, the greedy token, and the one that we chose. Okay, so it's kind of figured how far away in terms of this log probability measure are we when we make a choice. So our experimental setup is we looked at 3 different tasks, multiple data set, completely different data sets, different tool kits, and different evaluation metrics. Because we were interested in the search side of things, we wanted to go as widely as we can in terms of the actual tasks we were looking at. And so we have machine translation, summarization, and some image captioning. And the first thing we did was we started looking at the search, well, not the first thing, the first interesting thing we did, the first thing I can talk about that we did, is to look at the distribution of the search discrepancies. And so what this is showing is over a large number of problem instances, we look at the solution, the highest probability solution that gets spit out at the end, and we compare it at each point to what the greedy heuristic would have done at that point, okay? And look at where the discrepancies have occurred. And what we're seeing is as we increase the beam size, right, the discrepancies are disproportionately at the first couple of tokens, okay? Which is interesting, and those of you who know about tree search, hopefully there's some lights going off. We can also look at the discrepancy gap, okay? And again, as we increase the beam size, the discrepancy gaps, the bigger discrepancies, are disproportionately in the first few tokens. Okay? So our first observation is increasing the beam size leads to the solution chosen has more early discrepancies, okay? Disproportionately large early discrepancies. And so another way to think about this is the high probability solutions with a big beam size tend not to share suffixes with the high probability solutions with a shorter beam size. Okay. So the next slide is what really sold me on this, and of course it's Eldon who came up with this. He decided to take this graph, or actually this graph first, and say, well, if we look at these, we actually want to understand which of these actually led to a better evaluated solution compared to the greedy heuristic, and which of them led to a worse evaluated solution compared to the greedy heuristic. And so that's this. And so the green, okay, is the improved solutions. So that there are solutions that have a discrepancy at point 1, okay, that when we get to the end have actually improved over what the greedy heuristic would have given us, okay? And the orange ones are the ones that have degraded in our evaluation against that, okay? And what you see again is as we increase the size of the beam, disproportionately, well, we already know we've got more discrepancies at the beginning, but in fact, most of them lead to worse evaluated solutions at the end, okay? And we can show you the same thing in discrepancy gap, okay? And so the degraded solutions are disproportionately due to early large discrepancies. And those of you who know about the early mistake in tree search, this is something people have been talking about for a long time. Once we make an early mistake, right, we have an awful lot of effort to get out of that failed subtree. We're not getting out of subtrees here because of this beam search. We never backtrack. But what it's actually leading to is these higher probability solutions that don't really evaluate very well. Another way to look at this is if I'm taking an early discrepancy, okay, so these are the ones that have made things worse. If I take a low probability token at the beginning, I need some higher probability tokens later on, higher joint probability tokens later on, to actually compensate for that, for this sentence to come out as the highest probability. The example, so this is just an example of what we saw in the data. there's a broader, so this characterizes a broader set of examples. But one of the examples in the English to German translation was that in some of the training instances, the English sentence was what was given, the actual translation was an English sentence. Okay, so there was noise in our training data. And what happened is, if we had a big enough big enough beam, what would happen is that the German translation within our beam of that first token was an English word, right? And as soon as we pick that English word as our first token, with extremely high probability, the second token is an English word, and the third token is an English word, okay? And so what happened is we saw exactly this, right? We had a wide enough beam to take a bad decision at the beginning, okay? And then after that, we're in a point in the search space where if you're conditioned on that bad decision, there's only one or only English words that you can take after that, and so we're going to do that as the highest probability. But that was just one example. So no new algorithms. What we're going to do is we're going to artificially limit either the gap or the size of the gap, or the size of the gap or the rank within our ranks. And what we can do is show, so the baseline, okay, is what I showed you before. And in a number of cases, we were able to, by artificially limiting the actual amount of gap we do, we can actually reduce, and in some cases resolve this beam degradation. Okay. So the bigger beams led to an increasingly unlikely early token compensated by tokens with much higher conditional probability. This is a different kind of local optima. Okay. One way that this could be explained is we got into this low probability first decision, put us into a search space where we had a whole bunch of very high probability next decisions that filled up our beam. Okay. Because we're doing beam search, the alternative is that we didn't have a local optima that filled up our beam. We just have one point that fills up one element of our beam, right? And so there's no need to fill up our entire beam. We can actually have good options in the rest of our beam, okay? But because this highest probability keeps going in terms of this joint probability as we go deeper and deeper, that's still sticking there in our beam forever. And we have this different kind of local optima that's specific to beam search, okay? And so I think one of the things that I want to understand is what these local optimas look like as we change the search to something like beam search. We haven't published this idea of what these local optima look like. Our preliminary data is exactly what I've just told you in terms of what's going on. We are seeing this one highest probability hypothesis as opposed to everything falls into this bad area. Okay, where do I want to finish? Okay, so the probabilities predicted by the neural network are viewed as heuristic that guides the search. I think that's a completely natural way to look at things from our perspective. I don't think the machine learning people particularly look at things that way. I'm not sure it's 100% the right way to look at things, but I think it is an interesting way to look at things that might make give some ideas to this community. That is the extent to which we can drive the search, think about the search and the performance of the machine learning algorithms as a search. And further investigation of this connection, I'm hoping, will bring some insight. If we look at the overall system of the machine learning systems, right, we have this production at the end. Right? It's a key part of what they're doing, and to me it's fundamentally a search problem that maybe we can spend some time contributing to. So, some final words in terms of the work I've talked about and some of the ideas that might be interesting going forward. I live in these two worlds, sort of this state-based search and this constraint-based search, and one of the things I'm interested in is the relationship between them, both search and at a knowledge representation level. And I think that there are a lot of fundamental commonalities between these versions of search that we have yet to understand and that can contribute to the cross-fertilization. I also think there's some interesting differences. I haven't managed to figure out what a plateau would look like in tree search. If you think about tree and depths in trees, you can't, plateaus don't look realistic. And so I also think there's stuff going on in terms of GBFS when we have plateaus, and that whole relationship between H depth and the size of the local optima isn't going to show up everywhere, especially when we have plateaus. At least that's my hypothesis. Interestingly, the search that neural sequence decoding methods use is called inference, which, especially if you're a CP person, is really hard, because we have search and inference, and they've what they're calling search, what they're calling inference, we call search. And so I think that there's also more to do in terms of the beam search in planning, right? Plans are often sequences, and so I think there's more overlap here. And of course, in fact, there's people who are doing that work here. So Alan Fern and Sven Koenig are looking at beam search and planning, and so I think it's time for it to come back again and see what we can do now. The final thing I wanted to say is this idea of empirical algorithmics, that we spend an awful lot of time running problem instances, trying to visualize the results of the problem instances, trying to understand what's going on. And this is something that is in this community. There was a paper yesterday on parallel GBFS, which is doing very much the same sort of thing. And I want to encourage it and make it, maybe raise the importance of this in the community. It's harder for reviewers. Sometimes it's hard to publish these papers because we don't actually have a new algorithm that does something better. We've sort of provided a different understanding that people will argue with our understanding, and sometimes the reviewers will argue with our understanding. And so sometimes we have problems publishing these because we can't show a nice graph that shows an improvement in the search performance on problems that somebody is interested in. But I think it's important work, and I would encourage both the authors and reviewers to think about doing this type of work. And that's where I'll end.
We have time for short questions.
Yes, when you were talking about the problems with beam search, the thing that occurred to me, and I'm sure there must be something wrong with this, or you would have mentioned it, is instead of doing, say, a beam search with a beam size of 25, why not do 25 random restart searches with a beam size of 1?
So yes, we're thinking about how to do that. It's not as straightforward as it was for GBFS. We are seeing some results where it works and some results where it doesn't work. And so that's active ongoing research to understand what we did in the first half in terms of getting rid of that. Can we map it in? One of the interesting issues is that the beam search problem that they're doing, the neural sequence decoding, they don't have a goal, right? And if you think about what we were doing in GBFS, because we were looking for a goal, when we were off in a local minima, we had to get out of that. In this case, they're not in a local, they're in a local minima, but they're not going to get out. They're just going to find a bad solution, okay? And so there's some subtleties going on in terms of whether we have a goal or not, and we haven't completely worked out how to do the randomized restart. It's not as easy as it was with GBFS.
Thank you.
Thanks a lot, Chris, for a really fascinating talk. I want to ask you about your interpretation of local minima. You said something that I thought was quite evocative. The way that you define local minima for GBFS has to do with the heuristic evaluation function. And you talked about the ways in which what you found was sort of generic across heuristic evaluation functions. If you threw the heuristic away, if you just looked at the state space, you could ask yourself the question, are the behaviors that you're seeing a function of the paths through the state space from where you are to where you would like to go? And is that a clue to the invariance that both folks in the 90s found and what you found? What do you think about that?
So I'm not sure I understand what you mean by the structure of the paths from where you are and where you want to go. So I'd have to think more about that. my immediate reaction is I don't really understand how to define a local optima if I throw away the heuristic values, because the heuristic value is essentially defines the local optima. Okay, and I have arguments with Eldon over this multiple times, but really the local optima is, even if I go back to, say, local search as opposed to tree search, where I can think of the cost of, so my objective function, and I can think of a landscape, okay? The local optima is defined by an interaction between the search moves, right, and the cost function. So the search moves, what is my neighbor, defines the local optima, or it interacts with the cost function to define a local optima. In the same way here, that when I'm doing tree search, a local optima is this hole I fall into while I'm doing search. And so it's fundamentally coming out of the fact that I have this search process going on and I'm encountering these states that have this heuristic value. And so I can't analyze the local optima without talking about the search that's on this search space. And so maybe, in fact, this is the direction that you're leading in. But you can't untangle the heuristic and, in fact, the path from the local optima. Or at least I haven't figured out how to do that.
Okay, thank you very much, Chris.